Now, as I mentioned earlier in the previous lecture, in this part of the course, all the way till lecture 11, we're studying analysis techniques. We already finished asymptotic analysis, which is the underlying kind of theory or approach to code analysis. And we are going to start now looking at the different techniques to analyze code or any algorithm for that purpose. Now, we are going to divide the techniques we're going to study into two groups. The first group is concerned with iterative code or iterative algorithms. So here there is no recursion. The code is just a listing of for loops, while loops, do statements, if statements nested all together. And we will see three techniques: summations, amortized analysis, and randomized analysis. And then later on, we're going to see three more techniques for covering recursive code. So this split between iterative algorithms analysis and recursive algorithms analysis is really a must, because the way we think of recursive code is completely different from thinking of iterative code. And I'm sure when you started to learn recursion many years back in your computer science education, you felt recursion is different. And indeed it is different in terms of how it progresses in the execution of the code. The code is usually more compact, more self-defined, so you're defining the code in terms of itself in certain aspects. And consequently, when we analyze the code, because we don't have any loops, we don't have any nested if statements inside loops, the techniques we're going to use are going to be different, and they will rely more on mathematical findings. Don't underestimate as well the use of mathematics in iterative algorithm analysis. It's still heavily used, but the approach, as you will see, is quite different. So let's start by the first one, which is analyzing an iterative code or an iterative algorithm using summations. So here are the steps that you need to follow to analyze any iterative algorithm using the summations notation. Now, first I would like to explain why are we using summations. Because summations actually is a good mathematical technique to talk about the number of steps a specific algorithm takes. Now, why it's the case? Because all algorithms beyond the naive ones will have some kind of loop. And perhaps there are nested loops, and more common you will see if statements inside loops. And it turns out that if we are trying to count the number of steps an algorithm is taking, this is almost like writing a summation for what happens to the loop variables, or how many times the loop variables are accessed. It will turn out to be the same thing. So here are the steps, and we will see examples, and the picture kind of will be put together for you once you see the examples. So I'm going to read the steps. It says, in the first step, you assign each statement a term, a constant, or a summation. So you look at the algorithm steps or the code given, and for every line, you either assign that line a constant cost, or if it's a for loop, while loop, do loop, any form of iteration, any iterative construct, you are going to write a summation for it. Okay? Now, a summation, as you remember from your math courses, needs some start and end limits, and you will find that from the loop variable values, the values that the variable take from beginning to end, and their count. Both of them are important. Okay? Now, because remember, we are counting steps of execution, so it is important to consider the count of the values that the variable is going to take, the count of the values. It makes a difference, whether you are doing 50 steps versus 500 steps. Okay, and it slightly affects what happens inside the block of the loop, what range you take. So you need to consider the range for that purpose. Are you going from 0 to 500 or 500 to 1000? Okay, in both cases you are doing the same count. 0 to 500 is 500, 500 to 1000 is 500. But since the values are different, what happens inside the for loop or this looping construct you're considering, whether it's for loop or while loop or do while, what happens inside will change based on the range of values you're going through. Perhaps if you go from 0 to 500 in a loop, then the inside of the loop will be executed 10 times. While if you go from 500 to 1000, the inside of the loop will be executed 50 times. So you need to consider the count and the range of values. Now, after you pass through the code, writing constants or summations on the different pieces of the code, you are going to rewrite everything you've done as a polynomial form. And then next, we are going to simplify the polynomial that we have came up with by using summation rules. Then we are going to take away the constants, and then we're going to sort by the largest rate of growth. Okay? And we will use that as the big O of the algorithm. So let me show you an example. But before we jump to the example, I would like to remind you with the 4 most important rules we usually need when we analyze an iterative algorithm using summation. Now, these are not all the rules we will ever need. I have put here a link to a Wikipedia page that has the rest of the rules that you need to be aware of for summations. For most of the cases when I give you a quiz problem or an exam problem, if they are not these 4 rules, I would supply an 8 sheet in the exam or the quiz that includes the rules that you might want to consider as well, in addition to those 4. Now, but you need to know how to use not just these 4, but the rest of the ones in the summations, because in the exam or the quiz you will have little time to figure out how to use it if you have not seen it before. Okay, so let me go over the rules and discuss why are these like the most important ones and why they're so common. So in rule number 1, you have a summation that goes from 1 to n of a constant. What that means is you are repeating over the constant n times. Okay, and you will see this being used inside simple for loops. Now, so I mean by a simple for loop that will go from 1 to n, and there's only a constant work inside the for loop. We also have second rule, which states that the summation of w from 1 to n for a plus b could be solved as 2 summations, one on a and one on b. And this will enable us to break or to analyze nested loops easier, because we could work every one of the nested loops separately. Okay? Now, the third one says the summation of w equal to 1 to n, w multiplied by constant. I can take the constant out and just work it out as a summation on w. Okay? The fourth one says that the summation of 1 to n of w is equivalent to the computation on the right side, which will turn to be another important rule, because this is actually how we end up finding the actual asymptotic order, because we're not particularly interested in summations. We're just using them to count the number of steps, but at the end I would like to come up with a term in n, like n squared, n cubed, and so on. So I would like to solve this summation and ultimately get rid of my summations in the polynomial form I'm going to work with, so that I'm only left with some ends, and this will be rule number 4 will be our aid in doing that. So let's see a simple example first before seeing a more complex logic. So here I have a function called sum that takes some data, returns an integer. It initializes a local variable result with 0, and then I have one for loop with one statement inside it. The for loop goes from 0 to n. And the incrementation, and always note the incrementation in the for loop because this is related to the count of the values you're going to be working with. So if the I is equal to I plus 2, or I plus 3, or I plus 4, or I plus 5, you're going to get a different count of values because the for loop is going to execute a different number of times based on how fast you jump, and this is related to the incrementation in the for loop header. Now, what it goes inside the for loop is very simple. Actually, I am using the result to accumulate the values that exist in this past array. So it has data, between square brackets of I, and that means this is an array. I'm basically summing up the values in the past array, and that's why the method is called sum, and then I return the sum at the end. Now, obviously this is going to be O of n if you think of it by intuition, but here we're going to stop using our intuition because we want to use summations. And you might ask, like, why are we caring? We know how to figure it out by looking at the code. And my answer is going to be, well, wait for the practice assignments. You will see some nested for loops, problems with nested for loops, where when you look at the code, you would think that perhaps it's O of n to the 4, and then when you actually do the summations exercise, you'll discover that it's actually O of n to the 3, or O of n squared even, or sometimes n log n. So it is not always that simple to look at the code and figure out by intuition, this is the big O of this code, okay? That's really an exaggerated assumption on your ability to intuitively reach to the performance of a piece of code. And that's why I'm teaching you summations, because this is actually what you should be using all the time. Don't trust your intuition regarding code or algorithms. Okay, usually it was medium to complex algorithms, your intuition will give you a wrong result. So this is a more systematic way, basically. And okay, what I'm going to do is I'm going to go to every one of those lines, and as I mentioned, either I assign a constant or a summation term. I will look at the line and see what's going on there. Line number 1, I'm assigning a value to result. That will take a constant amount of time. It's not dependent on the size of the data, which is the array that's getting passed or being processed. So that's a constant. So L1 cost is constant. Okay. Now, line 2, I have a for loop. Once I see a for loop, any iteration, construct, for loop, while loop, do while, and so on, I'm gonna write a summation. Now, what's inside the for loop will determine what's inside the summation. Inside the summation, which is inside the for loop, line number 3, there is a constant work being done, which is accessing one element from the array. So that's independent from the size of the array. So it's a constant. Now I need to figure out what are the bounds on my summation. So basically, I have this n that goes from 0 to n, which means it's doing it n times. Okay, because we're counting the 0. So if big N is 5, then it's going to be 0, 1, 2, 3, 4. So it's going to be 5. The count is 5. So I'm going to say this starts from 1 to n, because remember in the summation, if you remember from your math days, it's inclusive, the term that appears on the top of the summation. It's going to be from 1 to n, or capital N. And then I have line number 4, I'm returning the result. That's again not related to the size of the data, so that's a constant. So now I have a constant plus a summation plus a constant. So the next step we're going to do is I'm going to rewrite all of this is in terms of polynomials. So it's going to be 2 constants, 2 c's, multiplied by n to the 0, which is 1, plus 1c multiplied by n to the 1. Where did I get this term, the second one? I'm getting it from resolving the constant using the rule that I was just discussing with you earlier. So I will take the constant out and I will resolve, and that will be I'm doing the constant n times, which is exactly what the for loop is spelling out. Now, 2c plus n to the 0, that's a constant multiplied by a 1. So that's basically a constant. So I'm just gonna, I'm just gonna say this is 1. It's a constant. I could keep it as a constant. I'm just gonna, write it as a 1 because 1 is a constant. And c multiplied by n to the 1 is n to the 1. Okay, because again, constant multiplied by n is still n. So really we're talking here about n. So this is O of n. Okay, this is how we actually work it out using summations. Now, here's a very, very important guideline which makes the summation methods very interesting. You got the basic idea. We're going to write either constant or a summation for every line we have in the algorithm, or every step we have in the algorithm, or every line we have in the code. If we have nested for loops, we should be doing the same, because we're applying this technique on the whole algorithm. So we don't bother if we have a for loop inside a for loop inside a for loop. It's going to be a summation inside a summation inside a summation, and then we solve summations. But here is an issue, and this is really the only trick with this technique. When you write a summation, you are actually writing the number of times the for loop is running. And if you have a for loop nested inside another for loop, the number of times the inside for loop runs is bound by or controlled by the number of times the outside for loop runs. But usually there are common loop variables between outside for loops and inside for loops. Okay, like I could use I in the outside for loop here, and I could use it somehow in the inside for loop. Now, as a limit, I don't want to cross it basically. Now, what that really means, or what that amounts to, is that the lifetime, and this is really the important part, the lifetime of the for loops are not all the same. It is not necessarily true that with every iteration of the outside for loop, all the inside for loops will execute. What that amounts to, or what that yields to, is that the inside for loop's lifetime and outside for loop's lifetime could change or could differ. And this is what I try to highlight here with these blue lines. The outside for loop will run, say, from 1 to 100. The first inside loop could run from 1 to 30. The second inside for loop, nested for loop, could be running from 1 to 40. The third nested for loop could run from 1 to 60. So when you write actually summations, you will have to make sure that you are running, or you are counting the number of steps in relation to the outside one. So you might ask, how can we do that? And it turns out, if you use summations properly, summations will work for you. You just have to make sure that whenever you write a summation, the loop is actually active that you're writing the summation for. So for example, if you look at the second line from the top here that goes from 1 to 30, I really want to represent the running count of 30 times, because after the 30th time, this loop will never run. Consequently, I cannot nest it inside a loop that runs from 1 to 100, which is the outside, for loop, because this is not running 100 times, this is running 30 times. Similarly, for the third line, representing the lifetime of the second nested for loop, it's going from 1 to 40. It's doing something 40 times. So I cannot, again, just nest it inside a loop that goes from 1 to 100, because this is not running 40 times. This is not running 100 times. This is running 40 times. So the way to go about it is that you have to inspect the lifetime of the loops, which means you have to figure out the number of times actually they do indeed run, and from what range to what range. And then you're going to make as the simplest way to go about it, you can make a drawing like the one I have put here. Identify the regions or counts or ranges that are common between all the loops you're looking at for a specific group of nested loops inside and outside, inside a bigger for loop like the ones we're looking at here. So you'll make this chart for every one of those for every loop that has nested for loops inside it. And you're making this just to make sure that you understand when is every loop active. And then what you do is you write a summation for every region there was a all or a group of them active. And this is why I have put these dotted lines. So you see the first for loop that goes from 1 to 100, I will just consider the first 30 runs of it, because in those first 30 runs, the second for loop, which is the first nested one, is also running. The third for loop, which is the second nested for loop, is also running. It's running from 1 to 40, but I will consider its first 30 runs at this time. And then the last for loop I will also consider from 1 to 30. So I will write a summation that appears here in red for this portion where all the for loops are running. And then I will write a summation for, which is the summation that appears here in blue, for the first and third and fourth line. So the nice thing about this is that the count is going to be correct. In the first for loop, the one that goes from 1 to 100, there is 10 of them running. And in the fourth, there is 10 of them running. And in the third, there is 10 of them running. Okay, the count is, we're doing 10 runs basically. Okay, so I'm going to talk about that as one summation. And then another one for the first and the fourth, and then finally the remainder of the first one where the inner for loops are not running, I will write a separate summation for it to count the steps. So this is how we go about it. So let's check this second example where I have two nested for loops, but the work done with the loop variables makes analyzing the execution of those two nested for loops a little bit more complex than what we have seen before. So the outside for loop goes from 0, I goes from 0 all the way till 2n. So if I start with n being 10, then I will go from 0 to 20. But notice in the incrementation part, I'm doing I plus or equal 2. So I'm incrementing I by 2 with every iteration of this outside for loop. What this means that the values I is going to take is going to be 0, 2, 4, 6, 8, and so on. And if my n is 10, then it's going to be 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and then I stop because it's less than 2n, not less than or equal. Now if you've counted what I'm just saying, or you just look at the line at the bottom where I list the values I is going to take, it's still 10. The steps are still 10. This loop will execute 10 times, not 20 times, because I'm jumping I by 2 every time. I'm incrementing I by 2, not by 1. And this is why it's important you understand the number of steps, or the count of the number of times the for loop or the loop executes, and the range of the values. So the count here is 10. I will execute this loop 10 times, but the range is from 0 to 20. Okay, now let's go and look inside the next for loop body, or sorry, header. So J goes always starting from n. So regardless of how many times this for loop starts or runs, J will always take the value 10, because J is equal to 10 in the initialization. And then I go in the condition J greater than I, but remember I is changing in the outside for loop. I'm incrementing it always by 2, and then j minus minus. So I always start from 10 and decrease. Okay? Now the question is how many times j will be assigned a value, and the answer is just 5. Because I is growing very quickly by adding 2 to it, so quickly we will reach to the condition or where j is not greater than I will become greater than j, which means I will become greater than 10, because j always starts from 10 if n is equal to 10. Consequently, the number of times j will be assigned the value 10, or the number of times this loop will execute, is going to be 5. That's in the case of n being 10, so it's going to be 5. And the range varies, because one time we will run the inner for loop from j to 0, from 10 to 0, and the next time is going to be from 10 to 2, and then the next time is going to be from 10 to 4, and it goes like this. Okay? So I have the next slide as well, just to make sure that we are on the same page with what's going on here with the inner for loop. So let's check that. So this is a trace, if you'd like, of the values of I and j. The code is still the same. I modified it a little bit. You see it at the bottom of the screen. I just added print statements so that I can display the I and the j. Now you notice the I is when it's 0, when we go inside the program running for the first time, the j will go all the way from 10 to 1, because the j starts from 10, and as long as it's greater than I, which is greater than 0, we will keep decrementing and printing, and we're just starting I with 0, so we'll go from 10 to 1. Now, the next time we run this for loop, we're going to increment I by 2, so I is going to become 2, so j will run from 10 to 3, and then j will run in the next iteration, the third iteration, from 10 to 5, because we made I 4, and then j will run from 10 to 7, and then 10 to 9, and then j disappears. We will pass through the outside for loop, incrementing I by 2, so I is 10, I is 12, I is 14, I is 16, I is 18, and in all of these runs the inner for loop is not executing, because we start with initializing j with n, and since n is 10, we will assign j to 10, or assign 10 to j, and then the condition will fail. 10 is not greater than 10, because I now reaches 10. And then 10 is not greater than 12, 10 is not greater than, or j not greater than 14, 16, 18. So in all of these where, I is 10, 12, 14, 16, in all of these runs, j is not executing at all. Okay? So let's do our technique blindly first. So this is what you're going to do. I will check every line. If it's a constant, say a constant. If it's a for loop, it's an iteration, any kind of iteration construct, then assign a summation. I will go to the outside for loop and say, okay, this is going on from 1 to 2n by 2. This is exactly what the loop is saying. I will multiply n by 2, and I will divide by 2, because I'm multiplying by 2. This is in the condition. This is my stopping condition, and I need to code that in my limiting term in the summation. But also, since the summation here is representing the number of steps, or the count of the different values the loop variable I will take, and since I am jumping in the with the loop variable 2 at a time, I will divide 2 multiplied by m, I will divide it by 2 to get the exact count of the values I is taking. So it's going to be 10 basically. And if n is 10, because 2 multiplied by n divided by 2, it means simply it's n. But I would like you always to code it this way, because sometimes the incrementation is not going to be the same as what you're multiplying with in the condition. So I could be having like I less than 5 multiplied by n, and then I equal to I plus 100. Okay, so what you see in the for loop header, you put as the upper term in the summation. Okay. Now we go to the inside for loop. So obviously this will resolve to I from 1 equal to n, the outside for loop I mean. Now let's go to the inside for loop. So what you're having in the inside for loop, the foo, I will assume it's a constant, okay? If I have got a term for it, like this is O of n log n, I would just plug that in inside the summation. But here I'm assuming foo is going to do constant work, okay? So I go from j equal to 1 to what? What I'm doing here, again in the summation, we are trying to represent, or we represent the number of steps or the count of the values that j is going to take. And the summation always starts from 1, okay? So the fact that we can write in programming the for loop to decrement by going from the upper term and then decrementing by doing j minus minus, we're not going to do that in the summation. This is mathematical summation, just like what you've studied before in your math courses. So we start from 1 up to some value to do the count, okay? Now, the question is, what can you actually write as the upper term for this inner for loop? So my first attempt is going to be just try to do a one-to-one mapping between what I'm seeing and in terms of the manipulation of the loop variable and the upper term in the summation. So I will say the following, it's going to be n, the total number of steps I could do. Okay, remember our n here is 10. N minus I minus 1 multiplied by 2. Now, why multiplied by 2? Because I is jumping by 2. I'm always saying I equal to I plus 2. So I'm trying to represent that. And now why I minus 1? Because I'm starting always from 0. So I would like to capture that execution as well. Okay, so this will be my attempt, and if you look at the bottom, this will be what I try to solve. The outside summation goes from I equal to 1 to n. Okay, that's the 10 steps basically we described earlier, from 0 to 20 jumping by 2 every for loop run from the outside for the outside for loop. And in the inside summation I have j equal to 1, and that's the number of steps that is going, j for loop is going to make in relation to the n, and in relation also to the I, okay? Because the I is actually the loop, the variable used in the outside summation. But this term has a problem. Mathematically speaking, this term has a problem. The problem is we cannot sum negative counts, because when I crosses n by 2, the upper term here will be negative, right? When I crosses n by 2, for example, if n is 10 and I is 6, or let's say I is 7, okay? Now, so it's going to be 10. Work out the upper term for the inner summation. It's going to be 10 minus 7 minus 1. That's a 6 multiplied by 2. That's a 12. So we're talking about 10 minus 12. That's minus 2. That has no meaningful solution using summations. You cannot say j equal to 1 from 1 to minus 2. Okay? Now, even though the upper term here in the inner summation kind of follows the logic of the code, it's not respecting the mathematical rules, so we cannot really solve it using summations now. Okay? So we need to figure something out to do about this. We need to do something about this. And this is what I was just saying, that this will resolve to minus 2. Okay? So we can't solve this mathematically, but we need to use summations to do the analysis. So this will take us back to this image that we described earlier, or this idea that we have to be very careful about when the loop is running and when the loop is not running. You write a summation to represent when the loop is running. When it's not running, you have to exclude it from the picture, and you cannot just write a nested set of summations with with nested for loops that have common loop variables, which means they will have different lifetimes, and expect to be able to solve it mathematically. Okay? We will not be able to solve it then. So the problem again comes from that we just mapped the code to the summation terms. Let's try to do something else. Let's try to apply our technique to figure out when is this nested for loop active and when it is not, and write a summation for the period of time it is actually active. And that's what you start seeing here at the bottom. I have split my summation into two portions, and the one on the left is representing when the outside for loop and the inside for loop, the I for loop and the J for loop, were both running. And then there will be a span of time where the outside for loop is only running and the inner for loop, the J for loop, is not running. So I write another summation for it. Now this makes perfect sense, okay? And this is something I could solve. So for the term on the left of the summation here, the difference is I am going from I equal to 1 to n by 2, which is the first half of the lifetime of the outside for loop, because in that lifetime, in that half, the J for loop was actually active. So now I'm properly counting the steps, okay? But I'm still left with half the runs for the outside for loop where J was outside the picture, it was not running. So I still represent it using the right hand side term here, that's right to the plus, where I go I equal to 1 up to n by 2, it's the second half of the steps. So if this is running 10 times, 5 times J was running, and another 5 times J was not running. So what's inside this summation is just a constant, okay, the one that appears on the right side. And this you can solve mathematically. Okay, so again, just to stress the idea, I'm considering the values and the range of values for the outside and the inside, and when both are running, I write a summation for it, and then the rest I write a separate summation for. Now, we didn't really finish. Now we have to solve all of this, okay? We got this nested summation term with some interesting upper terms, and you got the right side summation term as well. This is how I'm going to go about solving this summation term. So I will apply the rules that we've discussed before. I will try to get rid of the nested most summation first, and that's straightforward by applying rule number 1 that says that if you have a summation that goes from 1 to n on some constant c, it's the constant multiplied by n, or you're basically doing the constant n times. The innermost summation here, which is j equal to 1 till n minus I minus 1 multiplied by 2, I will think of all of this as the n, and consequently all of it will be placed multiplied by the c, and that's what you see in the second line here. I've just taken this upper term and multiplying it by the c. Okay, I could also use the same rule number 1 to handle or deal with the second term after the summation, which is I equal to 1 till n by 2 on a constant, because it's just going to be n by 2 multiplied by the constant using the same rule 1. And that's what you see in the third line to the right of the plus. Now for the left side of the plus, I'm going to use rule 3 to take the constant out. And now I have this term, which is a constant multiplied by I equal to 1 up till n divided by 2, and inside all of that is n minus I minus 1 multiplied by 2. Now in the next phase, what I'm going to do is I'm going to use rule 2. So the same line that we were discussing in the previous slide exists here as the top line in the slide. Now I'm going to use rule number 2 to distribute the summation on the term inside the brackets. So I will end up with constant multiplied by a summation of I equal to 1 to n by 2 on n minus I equal to 1 to n by 2 on I minus 1 multiplied by 2. And then on the right side of the plus, I have the same term that we've discussed before. Now the rest is straightforward math. I start to apply rule number 4, starting from the third line from the top, to get some answers, and I will keep doing that and resolve the fractions. And finally, as you see at the bottom, I have my answer as n squared. So the math here is a little bit more detailed. It's not difficult, as you probably already noticed. It's just some mathematical manipulations. All the manipulations here are done using the 4 rules I have showed you in the earlier lecture slide. And they're usually mostly used, and if there is anything else that you need, I will, as I indicated earlier, include it for you in an 8 sheet. But you should be able to go in a quiz or an exam, you should be able to go having the capability to solve such level of mathematical manipulation. Let's look at this third example with 3 for loops nested inside each other. Again, the approach should be, when we're doing summations, is to look at every loop and count the number of values that the loop variable gets assigned, and also inspect the range that the loop variable takes. This will pretty much give us everything we need to do the summation in terms of the lower limit and upper limit. What we need to check as well, to get a full picture of what's going on in the loop, is to check the incrementation part, how the loop variable is being incremented. And as you see here in this example, the loop variable is incremented by 1. So we're not going to fall into the issues that we've seen with the previous example. Now, also what we need to check in any given algorithm or any given piece of code, if the loop variable from one loop is being used in another loop. For example, here the I is being used in the second for loop. And this is what we need to worry about, if this usage actually will limit the lifetime of the second for loop. Now let's give them names. So the first one, I'm going to call it the I for loop, the second one is going to be the J for loop, and the third one is the K for loop. So checking the I for loop, I start with 1, I is initialized to 1, and it goes all the way till n squared, and it's getting incremented by 1 with every loop iteration. So basically we're going to do this for loop 20 times. I will take the values from 1 till 20 till n squared, which is going to be, if n is 5, is going to be 25. So I'm going to do 1 to n squared. J is going from 1 till I. So J is going a variable number of times with every run of the J for loop, depending on the I value. So the I value starts with 1, and then it becomes 2, becomes 3, becomes 4, all the way till n squared, and with every time J is running one more time, in addition to the previous number of runs it ran in the previous invocation. So the first time is going to run 1 time, the second time is going to run 2 times, the third time is going to run 3 times, and so on. The K for loop is quite simple. It goes from 1 to 6. So that's basically, it's not related, it's not dependent on I or J. It's not dependent on the previous 2 loops, apart from it being nested. And inside the K for loop, there is the sum plus plus, which is a constant. So the innermost summation is straightforward. It's going to be, from 1 to K, and we're doing a constant effort. Now, the question that remains, are I and J tied in a way that makes their lifetimes different? And the answer is no, actually, because J will run as long as I is running. The J for loop will run as long as the I for loop is running. There is no case here where the I for loop would run and the J for loop would not run. Okay? And inside the J for loop, we have the other summation. We will have the other summation for the K. So it looks like straightforward 3 nested summations. simply because the lifetimes are all bound. They will start and finish together, if you like to think of them that way. The first one runs from I to n squared. The second one runs from 1 to I. The third one runs from 1 to 6. Okay? And they are nested inside each other. So what I'm going to solve is a nested summation with 3's. And that's what you see here. I'm going I from 1 to n squared, nested inside it j 1 to I, nested inside it k 1 to 6. Okay? The last one is straightforward. It's going to be 6. Because if you do something 6 times, you're doing it 6 times. Okay? If you do a constant 6 times, you're doing it 6 times. So it's, just a 6. Okay? Take the 6 one out, the 6 out. Now I'm left with 2 summations. Okay? Now, going from j equal to 1 to I, and I have a constant, doing that constant time, or doing constant effort inside the summation, what that means is just I. Okay? Now, doing I equal to 1 n squared to n squared I on the I variable, that I could use rule number 4, and this would resolve to n squared multiplied by n squared plus 1 divided by 2. And the rest is just straightforward math. Okay? Now, the big O of this is O of n to the 4. Okay? This is something that, by intuition, you might or might not have reached to it. And the reason why is because you have here 3 for loops, while the performance is n to the 4. So the popular kind of idea that is completely wrong, that you have kind of probably heard of in CS3 or CS2 days in your early computer science courses, that if you see nested for loops, it's n squared. If you see 3 for loops, it's n cubed. And if you see 4 for loops, it's n to the 4. Is absolutely flawed. Here is an example where we have 3 for loops, and it's O of n to the 4. By this, we have finished the analysis using summations. As you have seen, it's a straightforward technique, requires some mathematical skill in solving summations, but there are really no fundamentally different idea than anything you have seen before. Now let's move on to the next one, which is going to be amortized analysis, which is slightly different approach that will require us to do some in-depth thinking about how we can do the analysis. So amortized analysis is done on an algorithm that uses amortization. And the question is, what is amortization? An amortized algorithm is a special kind of algorithm that behaves in 2 or more asymptotic orders. And I'm not referring here to best case versus worst case versus average case. I'm referring to, within the same case, if you like, there are 2 or more asymptotic orders. Sometimes it's fast, sometimes it's slow. We would often describe or think of the slow operation as being a heavy lifting operation that involves some extensive processing. And it will be at a higher asymptotic order from the more lighter ones. So if you'd like to look at the third bullet at the bottom, I'm showing you an example of what I'm referring to. For the same operation, for the same, say, worst case, you have the alternating sequence you're looking at. At one instance, the operation is n to the 4. But after we finish this n to the 4 operation, now I'm assuming here that we are invoking this algorithm with some data. So I invoke it with data set 1, and I get n to the 4 performance. And then later on, when I invoke it, I get log n. And then again log n, and again log n, and a stream of log n's, which is much better, obviously, than n to the 4. And then suddenly I get the n to the 4 operation again. So if you'd like to think of it on a graph where the y-axis is the execution time for invoking the operation or the algorithm, let's refer to it as the algorithm, not the specific operation of the two, but the execution time for invoking the algorithm. And as time progresses, which is the x-axis, from the beginning of time, once the algorithm starts running, what we are seeing if we model the execution time is a fluctuation that is very close in terms of numbers, and then suddenly a spike. So where the line is almost straight and closer to the x-axis, it's the log n. Okay. So the performance is going up and down, but very slightly, which is the area highlighted with the red ellipses. So this is all log n. And then the big spike is actually the n to the 4. Now, why would an algorithm ever need to behave like this? Whoever designed an amortized algorithm is thinking of the following, or is thinking along those lines, that we are going to do from time to time an expensive operation, a heavy lifting operation, to be able to get better performance afterwards. In other words, the heavy lifting operation is doing something that will stay with us in the internal details of the algorithm or the data structure we're working with. It's fixing things in a way, enhancing things in a way that enables the later on faster operations. So it's not by accident that we're getting a sequence of log n, log n, log n, log n, log n, log n. No, the n to the 4 operation in this example made it possible to get the log n later on when we invoke the algorithm. Obviously, if you invoke it once and you get n to the 4 and you never call or invoke this algorithm again, you're not making use of it. But if you're actually going to call it repeatedly, wouldn't it be nice if the algorithm is too complex, that you only get the bad performance every once in a while, and for the rest of the time until you get the bad performance again, you're getting a good performance. Okay? That's provided you can live with this type of behavior. I mean that the program, the software you're building it, or integrating this algorithm in, can tolerate having n to the 4 performance, once in a while. And then later on, you go back to log n. Obviously, log n is very nice. And obviously also, n to the 4 is not nice. N to the 4 is really slow. But, if you can tolerate that, then use such an algorithm. So any algorithm that uses this feature, which is called amortization, this notion of doing massive work followed by light work for a while, and then suddenly doing massive work again, and then again going back and doing light work because of the massive work you did. If you can actually design an algorithm like that, this is called an amortized algorithm. So what is amortized analysis? It's the analysis of amortized algorithms. Okay? Now, and again, this is used, I'm stressing the point here, when an operation runs in more than one asymptotic order. And they have to be asymptotically different. If an operation runs in 5 log n sometimes, and sometimes run in 60 log n, that's still log n. The condition here is it has to be a different asymptotic order. Okay? Now, the problem with this approach of algorithm design is that it makes the analysis a little bit harder. Because going to our example in the previous slide, if I have an algorithm that runs sometimes in n to the 4 and sometimes in log n, I cannot say it's n to the 4 and I cannot say it's log n. If I say log n, I'm completely ignoring n to the 4. And if I say n to the 4, it's not true because it will run only in n to the 4 every once in a while. So I cannot use summations, for example, on such an algorithm, because there will be parts of the algorithm that will get invoked every once in a while and will yield the summation of n to the 4, and the other parts of the algorithm that runs in the other times, it will yield the summation of log n. So I will end up with the same problem, n to the 4 and log n, or n and n squared, or n to the 7 and n to the 3. I have two terms, and I don't want to. When someone asks me, what is the performance of this algorithm, I tell them, well, okay, it might run in n to the 4 and sometimes, but that's not frequent, and most of the time it's going to be log n. But this is not an answer, okay? Because who guarantees what? Who guarantees whether it's going to be n to the 4 or log n? So there has to be a better way to talk about amortized algorithms. And the better way is to use amortized analysis, not the typical just plain summations like we've done before. So we're going to look at two techniques in amortized analysis. We're going to look at a method called the averaging method and another one called the accounting method or the banker's method. Okay? When to use which? If you would like to analyze one operation that is having an amortized behavior, which means one operation is having two asymptotic orders, okay? Two different asymptotic orders. So n to the 7 and n to the 2, or n squared. And it's one operation only, then you use the averaging method. But more commonly, if an algorithm or a data structure is using amortization, it will use it all over, which means, especially for a data structure, two or more operations in a data structure. Remember from CES 3 days, for any data structure there are three, at a minimum, basic operations. How you insert in the data structure, how you remove from the data structure, and how you search in the data structure. So typically, if a data structure is utilizing amortization, it will be utilizing amortization in the three operations: insert, delete, and search. So if you are analyzing two operations or more, what you do is you use the accounting method. But if it's only one operation, then stick to the averaging method. So here are the steps involved in the averaging method. Now, the first step involves identifying parameters describing the data structure and the operation at hand. What do I mean by parameters? I mean variables that you could use to express change or manipulations that happen during the operation or on the data structure the operation is performing on. Now, all operations will use some kind of data structure, even if it's an array. Talking about how much the array, for example, is full, or having a parameter that documents how much an array is full, is useful in understanding the behavior of the operation. If this is a tree, talking about the height of the tree. If this is a queue, talking about how many elements in the queue, okay, or the rate of insertion to deletions from the queue, or the rate of in-queues versus dequeues. So you have to come up with some way to quantify the behavior of the algorithm that is reflecting the changes that happen or the computations that happen. So here we are departing a bit from the notion that we're going to count the steps in the algorithm and compute it in terms of O of the size of the input. Okay, we are going back now to we're going forward now to another thing, which is identify parameters that reflects the changes that the algorithm is making or the operations, and use that. And obviously you're not going to come up with something out of the blue. What you need to understand is what the operations, what the algorithm is doing, or what operations are being done, on where are actually they are being done, which data structure. So an entry point to finding the parameters, or a technique to find the parameters, or a starting point to find the parameters is the data structure the algorithm is working on. Okay, it's going to be the size, the rate of how fast it gets filled, or any other related measure that you can identify. It sounds a little bit scary because you're going to look up for something and then use it later on in all the steps, but it is not. Usually this is an easy and straightforward step. Okay? Why? Because any algorithm will work on a data structure, even if it's just a simple array. So you can talk about the length of the array or use the length of the array if that is useful for your case. Now the second step is, and this is really where it starts to get a little bit hard. You gotta state your assumptions here. You're gonna and it is hard, but it's not as complicated as it sounds. The thing is, you have no control on the input that you will get, neither on the sequence of inputs that you will get. So you are not capable of predicting upfront the input so that you can say, okay, I'm gonna do a number of easy operations or log n operations followed by n to the 4 operations because I have this input. Since you cannot predict the input, you cannot predict when are you going to get the slow operation and when are you going to get the fast operation, or consequently, when are you going to get afterwards the fast operations. So you have to state some assumptions here. For example, a simple assumption could be, I'm going to start from an empty data structure. So I will kind of skip the historical part, so I don't have to worry about what happened before, because nothing happened before, because I'm just starting from an empty data structure. Okay? Now, the third point is, based on your assumptions, you have to come up with some observations about what do you expect to see because of the algorithm that you're studying. Okay, and really I always find students struggling with this point, so I'm going to show you a number of examples that will clarify what do we mean here by observations. Okay, you have to think about the operation of the algorithm starting from your assumptions. So you have control, you have freedom to state the assumptions, as long as they are realistic assumptions. Okay, and being realistic includes starting from an empty data structure, or nothing has happened before. Okay, now, so you will deduce some observations based on your assumptions. You will say, okay, if these assumptions are my starting point, or they are valid, and a number of these operations happen, the slow and fast, what would be my observation? Okay, what should I find inside the data structure I'm storing the data in, or what could have happened as a result of my slow and fast operations interleaving? Okay, now step number 4 really is you simulating what's going to happen. Okay, if your assumptions is I'm going to start from an empty one, or any other thing that is useful to you, you start to run it in step number 4 in simulation in your mind. Okay, so I'm going to start from an empty data structure, and I will assume my operations have been performed. And here I will not make any assumptions, or I will not make any claims about what are actually these I operations. They could be a pair of slow ones into the 4, and then the rest are all fast ones, or there could be 3 slow ones and the rest is fast ones, or there could be any combination. Okay, so I will assume that I operations have been performed, and then I stop the execution, and then I do step number 5, which is I will use the parameters that I have identified to calculate the time or the number of steps that were computed in these I operations, all of them together. Okay, in a holistic way, in the sense that I will not go and say, okay, if I have I, let's assume I is 5, let's compute what happened in the first one, and then the second one, and then the third one, and then the fourth one, and the fifth one, and then I got the I. No, we are actually going to develop in terms of I together, as you will see. Okay, now this next step is going to be straightforward. I will solve in terms of I. In other words, I will say that my big O is an order of I, not order of n, not order of the size of the input, it's order of I. I will basically develop a term in terms of I. So what I will have is the big O of some I. It could be like O of I squared, or O of log I, or O of I to the 3 plus I to the 2, whatever. Okay? So I'm talking about all of them as one bunch. And I got a big O of I as one bunch together. I don't know the individual performances within this bunch, but I know that together the performance is this big O of I. Now, since I'm interested in the performance of one, because when people talk about the performance of the algorithm, they are referring to one invocation. Okay, they are referring to a specific instance of running. O of I is not useful, is not a meaningful answer, because I would like to relate it to n. So the last step is actually quite trivial. It will be surprising to you. What I'm going to do is I'm going to divide by I, because if I divide by I should get it as the cost, the output, or the quotient is the cost of one operation, and that will be in order of n. Okay, so again, to recap, we are doing a little bit of an involved activity here. we are doing what's called the averaging method. The averaging method is used when you have an operation or an algorithm, one operation or one specific algorithm that has two or more running modes. One is fast and the other one is slow, where the difference between the fast and the slow is of an asymptotic nature. It's an asymptotic order difference, not a constant difference. It's an asymptotic difference. What we're going to do is that we are going to extract or come up with parameters that describes the operations or the data structure we are working with. And then we are going to state some assumptions. And then we are going to deduce some observations based on the parameters and the assumptions, or using the parameters and the assumptions. And then we will assume that I operations have been executed. And then we will compute the cost of running those I operations as one thing. And finally, we will divide by I to get the cost of one operation. Let's see an example. You have already studied a data structure that used amortization, which you learned in data structures. It's the hash table. Okay? Now, what are the hash table parameters, if you remember? You had big N, which is, or capital N, the number of buckets, and you had small n, which is the number of items that you have inserted into the hash table. And we also had a third parameter, which is the load factor, which is small n by capital N. The load factor was quite important because we told you then when you learn data structures is that you have to keep the load factor less than 0.75 to decrease the chance of collision and to always guarantee that you're getting the nice O of 1 performance, which is quite an amazing performance. What we didn't tell you then is actually the hash table is an amortized data structure. This is not a regular data structure, it's an amortized data structure. Okay? Now again, amortized data structure or amortized algorithm means that there are at least two running speeds or two different performances. So where is that in the hash table? Actually, all the operations of the hash table, the put and the get and the find, are amortized. So what we have actually told you before, that it is O of 1, is not entirely accurate. It's called amortized O of 1. Okay? Amortized O of 1 means it was obtained using amortized analysis. So I will here focus on the put alone, as if this is the only operation I have. I don't have a get, I don't have a find. Okay? Now, the put is amortized O of 1. And if I'm trying to analyze the performance here, I'm going to use the averaging method we were just describing. Why? Where is that actually happening in the hash table? Why is put having two different asymptotic orders? This has to do with the load factor. If you remember what was described about hash tables, is that we maintain the load factor so that when we cross the threshold of 0.75, we are going to resize the internal array inside the hash table to be double the size. So we go from n to 2n. And then we go and read all the entries in the old array and rehash it inside the new array or to the new array. So if the old array was 10, we usually would take at the end of the equation we are using to find the location for an item, mod 10. Now because the array size is 20, we're going to take mod 20, and this keeps going on. But this operation I'm just describing actually is not O of 1, this is O of n. when we cross the threshold of 0.75 and we decide to resize the buckets from n to 2n, that's not an O of 1 operation. I'm going to go and read all the entries, so that's O of n, and then rehash them and write them in the new bucket, or in the new buckets of size 2n. So that's one read and one write, so that's 2n actually. But we would simply ignore the constant, the 2, and we say it's O of n. So there is no O of 1 here, it's O of n. So this is the slow operation here. The fast operation is when you are below the threshold, below 0.75, the threshold we're computing from the number of entries divided by the total number of buckets. When you're less than 0.75, you don't double the size of the buckets, you just apply the hash function and go to the right bucket and grab the item and return the value. Okay, you get the key, you return the value, as typically it is in hash tables. So as long as we are below the threshold, we're running at O of 1. That's the fast version of the put. And once we cross the threshold, we are running now at O of n. That specific instance that where we cross the threshold, because we are resizing the bucket size from n to 2n, and later on from 2n to 4n, and later on from 4n to 8n, and so on. Okay, so it has two running speeds, if you like, or running asymptotic orders. The fast one is O of 1, the slow one is O of n. And for this, we would describe put as being an amortized algorithm. So let's apply the steps we discussed into analyzing put amortized behavior. The parameters for the hash table is straightforward. We already know that the important variables that determine what's happening inside the hash table is the n, the number of items that has been inserted, is the big N, which is the number of buckets that have been created or are currently active, and L, which is the load factor. In the assumptions part, I have the freedom to make any common sense or fair assumptions. As long as my assumptions are not extreme or not realistic, then I could work with the assumptions. I will assume that I have a new hash table with only one bucket. And I will also avoid doing my analysis with chains. So I will assume that the chains do not grow longer than 1. Now, for real, of course, if you analyze a hash table behavior, the chains will grow longer than 1. But this assumption is not an oversimplification, because whatever we find, we could scale it up by a constant to compensate for the chains growing up longer than 1. That's if we can prove that it is actually O of 1 amortized. And I will also assume that the put will take, in terms of the hashing function execution, less than 1 second or less than 1 unit of time. Okay? Just that my computation is going to be as simple as I can. And I will also make this assumption that the doubling of the buckets are going to happen when the load factor is equal to 1 instead of 0.75. Okay? Again, this is an assumption just to be able to work out the math, in a simpler, using simpler computations. We could still have done it with load factor equal to 0.75, but we're just going to complicate our math a little bit. And the assumption also, the last one, is that resizing takes 2n seconds. 1n for reading, 1n for writing. Okay? Or 2n units of time if you'd like. Okay? Now, I don't have to actually refer to these as seconds. I could just use them as 1 unit, or 1 equivalent to processing 1 value, okay? Or doing 1 computation. But I'm just trying to make it closer to your mind by using seconds, okay? So it makes sense, if I have n items, I'm going to take 2n seconds, one n to go through all the items from beginning to end, assuming that I'm accessing an item in a second. And I'm going to write each item again, so I'm going to go from 1 to n. So that's 1n, and 1n, that's 2n. Now, what about my observations? This is really the hardest part here, Okay, let's think about this. The behavior I'm interested in is the resizing, because this is really where things start to change from the norm. The norm is I hash a key, I get an index into the array, I retrieve the value, corresponding value to this key, and I'm done. This is the typical operation that you want to do a find or a delete, and the same idea follows for the put. You get a key, you'd like to insert it, you hash it, you get the index where this is supposed to insert, you insert it in the cell index where you're supposed to insert it in, you just go and put it there, okay? The different behavior comes from the doubling of the buckets. So I'm gonna focus on that. So I'm saying that resizing double n, thus for any given n, the sequence to reach there should be what I have written here. If I stop at one point, I will say what I have now is n buckets. Before that, I had n by 2, because I went from n by 2 to n by multiplying by 2, okay? And if I look at the hash table and I have 10 buckets now, let's say 20 buckets now, then I must have had before it 10, and I doubled the 10 to 5, to 10 to 20. And when I had 10, I must have had before it 5, because I doubled the 5 to 10. And this goes like that, okay? Now, but actually, because I'm always doubling, then the numbers should go from 1, and I'm starting from 1, should go to 2, because 1 multiplied by 2 is 2, and then 2 multiplied by 2 is 4, 1 multiplied by 2 is 8. So the sequence is going to be 1, 2, 4, 8, 16, 32, 64. I'm not going to see the value for capital N being 10, for example, because the doubling will take me through a specific series of numbers, okay? So this is an observation that makes sense. It kind of tells me a lot about how the big N grows. Another observation is that after I make a put, obviously N is going to be increased by 1, because I'm making a put, I'm increasing the number of elements in the hash table by 1. Now, I'm going to run I operations. The I operations are all of the same type, they are all put, because I'm analyzing only the put. So after I puts, I will have N equal to I, small n equal to I. Every one of these puts is a put, it's inserting one element. So if I run 10 times the put operation, regardless of whether it was executing in the slow mode or in the fast mode, I should have, after the 10 operations, 10 elements in the data structure. So my small n is going to be equal to I, okay? Now, this is really another important observation here, is that n is the smallest power of 2 that is greater than or equal to small n, or big N is the smallest power of 2 that is bigger than or equal to n. Perhaps out of all of these observations, this is the one that kind of students face difficulty understanding. If you look at the sequence of values that big N will take, it is jumping. It goes 1, 2, 4, 8, 16, 32, 64, and it goes like this. Between any two values of big N, between 8 and 16, we also have small n values, or small n entries. Okay? Now, if my load factor is 1 for me to do the doubling of the big N, when I reach to the 8, when the big N is equal to 8, then I must have 8 entries. Right? Because my load factor is small n by big N equal to 1, then I do the doubling. So when my big N is 8, also my small n is 8. When I double, I will take the big N to 16. But the small n will increase one at a time, so it will be 8, then 9, then 10, then 11, then 12, then 13, then 14, and so on. So that's why, because there is a relation between the big N and the small n, that the small n is jumping faster, but the big N is jumping faster, is making bigger increases. It goes 4, 8, 16, 32. The small n is following it. Okay, but the big N is not jumping like exponentially on the scale of numbers, leaving the small n behind. In fact, the relation between them is that the small n has to be relatively close to the big N, but the big N is advancing beyond it, because between the 8 and 16 there's a number of values that the small n needs to take, okay, which is 9, 10, 11, 12, and so on. So the big N is the smallest power of 2 possible that is greater than or equal to n. Okay? Now I want you to actually plug in some numbers so that you get a sense of this. How can it be that it's the smallest power of 2? So it's 2 to the power something that is greater than or equal to n. Okay? So if I say 16, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32. Okay? So I'll have to pick a power of 2 that is small enough that will bring it as close as possible to small n, because that will be the right value for big N. So in other words, we said 2 to the 2 is 4, 2 to the 3 is 8. If my small n is 9, then big N has to be 16, okay, which is 2 to the 4. And this is the smallest power of 2, in this case 4. 4 is the smallest power of 2 that will give you a number that is greater than or equal to n. Right? Common sense wise, it has to be, if small n is 9 or 10 or 11 or 12, then big N has to be 16. It cannot be 32. Okay? Because remember, we are going to do the reverse of what we're doing in terms of enlargement. If the number of entries in the hash table decreases beyond a quarter. So if small n by big N is less than 0.25, I will shrink the internal array of the hash table from n to half n. So I'm always keeping the number of buckets in relation to the number of items close. Okay? So just like I enlarge, because I need to reduce collisions, I don't want to waste space, so I'm going to cut the number of buckets by half if the load factor drops below a quarter. Okay, drops below 0.25. What that means is big N is always guaranteed to be the smallest power of 2 that is greater than or equal to n. Now we do the fourth step and the last point in this slide, which is the simulation part. I'm going to assume iputs run. Okay, I will assume that I have executed iputs. Now let's do the analysis. So all this, we're kind of preparing a model to be able to do the analysis. Our goal is to find how long it will take me to do iputs. Okay? Now, each put is either O of 1 or O of n. So the cost of iputs is the cost of I inserts plus the costs of resizing. So I will think of the O of n as involving a resizing activity and also an insert activity. I will group all the inserts together, and they will be, I will call them I inserts, because if I call put I times, I am inserting I elements, so I've made I inserts. That has a cost, okay? And then the other thing is the cost of the resizing, which is going from n to 2n to 4n to 8n and so on. Okay? So let's think of the resizing. The first one is easy. It's going to be I. The cost of I inserts is I, because we said every insert will take 1 unit of time, or if you'd like, 1 operation, 1 computation. So I'm just going to call it, if I do I of them, then I have I in total. The problem is in resizing. How can we calculate the cost of resizing? Okay, so this is what we're going to do. The last time we do a resizing is going to take us n seconds, because we said that the resizing is 2n. I'm just going to forget about the constant, the 2. I'm going to say n. Okay, so that's the last time, because I say the way we're thinking of this, I will run I operations, the simulation, and then I stop and say, okay, let me figure out how much time I took. So now I have in my hash table n buckets. So to build those n buckets from the previous bucket size, which was n by 2, it took me n seconds. proportional to the size of the buckets or the number of the buckets. Before the current status of n buckets, I also had to build the one before it. So let's say after the I operations, we stop at a hash table, or we now find that the hash table has 64 buckets. So to reconstruct or to construct those 64 buckets, I must have spent, according to my model, 64 seconds. Okay? Now, before I get 64 buckets, I had 32 buckets and I doubled them to become 64. So I also spent before that an interval of time equivalent to 32 units of time. And before that, I also stopped and did create 16 buckets, because I went from 16 to 32 to from 16 to 32 to 64. So also I spent some time creating at one point 16 buckets, because I was enlarging it from 8 to 16, and this goes on. This is what you see at the formula at the bottom. Okay, this is trying to sum up all the units of time, or all the operations that I did every time I was trying to do a resize. I started with 1 bucket, and then when the load factor reached 1, I resized it to 2. And so I spent some time doing that. And then I resized that to 4, so I spent some time doing that. And then I resized the 4 to 8, so I spent some time making up the 8 and then rehashing the values from the old to the new. And then 16, and then 32, and it goes like this all the way to the last n, which is what I currently have in after I operations. Okay? Now, this series has a sum. We know from calculus this has a sum. It's equivalent to 2n minus 2. All of these guys are equivalent to 2n minus 2. Okay, 2 big N minus 2. Again, the problem here is that to find out how much time it took me in terms of I, or in any terms, in terms of anything, how much time it took me to do I puts. Since I know what is happening, I'm inserting the value and I'm resizing, I split the insertion activities separately, and I can figure out quickly how, much this costs, because the insertion is not based on the size of the data. The insertion is based on computing a hash function. So if I'm doing it in a unit of time, that's acceptable, because this is a mathematical computation. And if I'm doing I of them, then I'm going to take I units of time. The problem is the resizing is a little bit complicated, because I did resizing many times. Okay? Starting from a bucket size of 1, I resized to 2, resized to 4, resized to 8, and it went like this. Okay? So I did many times. Now I need to factor in the cost of doing all of the resizes, but I don't know how many really they are. So I'm just going to talk about them in terms of the last size I have, which is the one I currently have after doing I puts, and that one I will assume it's being big N. Now before it, I must have done some work on n by 2, just like I have explained. Okay, so in total I have done 2n minus 2 units of time doing resizing. Okay, so what we are looking at now, the cost of I inserts is I, the cost of resizing is 2 big N minus 2. Now here is a problem. I don't like what I'm looking at now. I don't specifically like 2n minus 2. Why? Because this is big N, which is the number of buckets. Our goal is to make it in terms of I, so I can divide by I and I can get it in terms of n, small n, which is the number of entries. But this is the number of buckets. So we need to figure a way to actually remove the big N from our calculation here. So what I have now is O of I plus 2 big N minus 2, where big N is number of buckets. So what I'm going to do is I will replace the big N with 2i. This is the observation I spent some time talking about, that the big N is the smallest power of 2 that is greater than or equal to n. Okay? So if I'm looking for the worst case here, an upper bound, it cannot be bigger than twice n. Again, work out some numbers and you will see that it is indeed true. Okay? If you just try the example with 8 and 16. The number of buckets being 16, it means that you've definitely exceeded 8 entries. Because when you were at 8 entries and 8 buckets, the load factor went to 1, and that made you double the 8 buckets to 16 buckets and added 1 entry to the number of elements you have, so now it is 9. So the big N is the smallest power of 2, like I have explained before, that is greater than or equal to N, so it's going to be 2 to the 4, okay, equals big N. Now, if I'm trying to replace the big N with a value that is greater than it, to be on the safe side, but not much greater than it, from what I have, from the parameters I have identified, I can easily claim that big N will always be less than 2n, too small n. Right? Again, think of the example where I have the big N is 16, so we said the small n has to be either 9 or 10 or 11 or 12 or 13 or 14 or 15, because when we reach to 16, it will not be 16, because when we reach to 16 we're going to double again the number of buckets, so it's going to be from 9 to 15. So the big N has to be less than 2n. Okay, on one side you have n being small n being 9, so 2n is 18, so 16 is less than 18, and on the other extreme n could be 15, so 2n is going to be 30, 2 small n is going to be 30. So for sure big N is less than 2 small n. Okay, now, and it's going to be equal to 2i, right? Because if I get n entries because of I operations, because I'm inserting in every one of those I operations one key, so 2n is equal to 2i. In fact, 2n is because of 2i. So I will replace first big N with 2n, and then I will replace that with equivalent to saying also 2i. So it becomes I plus 2i minus 2, which is 5i minus 2. Okay, this is a worst case scenario. That's why I am pumping up the value for n. Okay, now, so to do I operations, it's going to be 5i minus 2. What about the cost of one operation? It's going to be 5i minus 2 divided by I. The I goes away with the I, and you end up with a constant. And this is actually what we refer to as amortized O of 1 calculation. Okay? It's on average. As you keep running this, put forever, you get slow followed by fasts, slow followed by fasts. So on average, you could say it's amortized O of 1. This is not a deterministic O of 1. It's an average O of 1. This is what we conclude. This is what you will see in textbooks, by the way, so you've learned something new. If you ever come across an algorithm and it tells you this is amortized O of 1, then first you need to understand that, number one, this algorithm is amortized, it involves amortization. Number two, amortized analysis was used to come up with this term, okay? And you will see this in your Corman textbook, and you will see this in the Goodrich and Tamassia textbook. It will be, described as amortized running time of put is in O of 1. And usually it will be just be written as amortized O of 1. Okay, so you know what this is talking about now. Let's look now at the second method we're going to study for analyzing amortized algorithms, which is the accounting method, or sometimes called the banker's method. Now, you use this if you are interested in analyzing the performance of two or more operations that are involving amortization. Why would you have two or more? Typically, this will be applied in the context of a data structure. As we mentioned, the Typical operations in a data structure should involve some way to insert values in the data structure, some way to retrieve values from the data structure, and some way to delete values from the data structure. So if you have a data structure that uses amortization and you would like to put a label on the overall performance of this data structure regardless of the operations that are being invoked, then you need to use the accounting method. So for example, you could claim that this data structure performance is amortized log n all the time. Whether you do insert or delete or find, it's always log n amortized. Now, this is a little bit more involved than the previous method, okay? And it involves some kind of modeling or imaginative thinking to actually understand what are we really trying to do here, okay? Now, we are still running with the assumption that every one of the operations involved will have an amortized behavior, which means there will be 2 costs for every operation. So I could run this method on 2 operations where everyone is having a slow and a fast version, or 3 or 4 or 5 operations, it doesn't matter, as long as each one of them is having a slow version and a fast version. The other thing we need to understand about this method is that it involves accumulating money into a bank account, or what we call the dollar concept, okay? You see, what we are actually after here is much more complex than what we have seen with the previous technique, because not only I cannot make any assumptions about which operation will run. Within every operation there are 2 versions. So if I'm analyzing this on just only 2 operations amortized, each one of the operations or functions have a slow and a fast version. I make no assumptions at all about anything in terms of who runs first or how frequent the slow operation will run, okay? Now, for that, this notion of accumulating money in a bank will turn out to be useful, because we will assume, as you will see, that a number of these operations have run, and then we ask ourselves, do we have to pay money for can we pay money for these operations from the bank? I'm just introducing the idea now, and you will see it like in bits and pieces as we go along. So what we're actually going to do is we will establish for each one of the 2 versions for every operation an actual cost and an amortized cost. Okay, the actual cost is the number of O of 1 time steps the operation perform. Okay, so this is related to what actually gets done. If you'd like to think of it in a very high level terms, an actual cost is what you actually execute, or the price you pay for actually executing an operation, whether it's fast or slow. Okay, the actual price you pay. The amortized cost is the amount of dollars you save by running a specific operation, which will vary from 0 to some number. And that's why it's often described as the amount of dollars you charge to the operation. Okay, so there is an imaginative model here that we're trying to build. In this imaginative model, we have money allocated to an operation. Either we spend the money or we spend portions of the money. If we spend the whole amount, we will charge that to the operation. If we spend part of the amount, the remainder is left in the bank. Now, why am I talking about 2 scenarios? Because remember, every one of our operations has 2 modes, a fast mode and a slow mode. So in the fast mode is asymptotically different from the slow mode, so we will assume the slow mode is consuming money and we're not saving anything. But when we actually start executing the fast mode operation, the fast version of the same operation, like the fast version of put that we were looking at, we are actually saving something. We are saving the difference between the fast and the slow. And we will accumulate that in the bank. Okay? This is what I try to highlight with the 3 bullets at the bottom. If the total amortized is greater than the total actual, we are in a good shape. If the total actual is greater than the total amortized, we are in a bad shape. And the bank balance should never drop below zero. What that means is, I'm going to draw to you an analogy. Let's say while in university, a student takes a pocket money from his parents, £100 a day. So at the end of the week, he had a chance of accumulating £500. And at the end of the month, he had a chance of accumulating £2,000 if he spends nothing. But he's going to spend some money. So if he spends nothing, he will have £200 at the end of the month. If he spends some, he will take away from this money. But let's say when he buys something, he actually does not pay from the money, he uses his credit card. And he must repay the whole amount at the end of the month. So there is no loaning system behind the credit card. It's a kind of zero loans credit card. Now, if at the end of the month what he spent is less than £2,000, let's say he spent £1,500, he will be able to pay that debt, because that debt is actually payable because he has £2,000 in the bank, and he's required to pay at the end of the month £1,500. So in fact, he will actually end up having an extra £500 at the end of the month. However, if he in a month bought items that are worth £3,000, what he's getting as a pocket money is £2,000 in a month. So at the end of the month, he will not be able to pay the £3,000. What we want to make sure while running an amortized algorithm that involves many operations, where every operation has two versions, is that we stop the program at the end and say, or at one point and say, okay, do we have money to pay this? And this is the essence of the accounting method, or the banker's method. Okay, now if we would run a simulation and then we stop and say, can we actually pay for what has been happening? Because if we can actually pay for what has been happening, this means that the fast operations are helping us by accumulating money in the bank. While the slow operation is taking money from the bank, the fast operation is taking less money from the bank. So there is a difference between the fast and the slow cost. And if we have been running the slow operation only a small number of times, and most of the time we're doing the fast operation, then we have been accumulating way more money that will enable us, which is the difference between the fast and the slow, that will enable us to pay for the total cost of all operations. Okay? So here is again the same scenario we were looking at, except I'm starting now to put some numbers. So let me read this bullet. It says, consider the following two scenarios for two operations. Each has two asymptotic bounds, fast O of 1 and slow O of n. Both have actual cost of $1 and amortized cost of $5. Okay? Now, S sub I refers to the slow mode of operation I. F sub I refers to the fast mode of operation I. Let's see the following. Let's say that we had the following interleaving of fast and slow versions of operation 1 and operation 2. So F sub 1 means operation 1, the fast version, F sub 2 means the fast version of operation 2, and then followed by F sub 1, which means the fast version of operation 1, then F sub 2, then S sub 1, which is the slow version of operation 1, followed by S sub 2, S, and then again S sub 2. So we did two slow versions of operation 2, and then two fast versions, one for operation 1, and we conclude, with operation 2, the fast version. Okay? Now, we allocate dollar values. We allocate two values. actual cost and amortized cost. Okay? The actual cost is what we actually spent. So for the fast version, I am going to allocate $1 to the fast version of operation 1 and operation 2. And I will pay $5 for the slow version of operation 1 and $5 also for the slow version of operation 2. What you see as the second line that says actual cost is the money we are paying, the price we pay to support each one of those operations. So since we start with a fast version of operation 1, we said the fast ones will cost us $1, so I'm paying $1, and then another $1, then a third $1, then a fourth $1, then comes the slow version of operation 1, and this cost me $5, so I have to pay $5. Then another slow one from operation 2, followed by another slow one from operation 2, so I pay again 2 5s, and finally I pay $1 and $1. So the total amount of money I paid to run this is $21. Okay? Now, how do I know I have money in the bank to pay for the $21? What we're going to do with every one of those operations, as we invoke it, we are going to calculate the money saved. The money saved is what is called the amortized cost of the operation minus the actual cost. So the amortized cost we said is going to be 5, okay? Which means at most we can pay $5 for an operation. And since that's at most, at minimum we're paying 1, which is the actual cost. Now, what that means is when I executed the fast version of operation 1, and instead of paying the 5 that was planned, that is hypothesized, I pay only 1, so I'm left with $4 I could spend later on. So I accumulate my spendings. Sorry, I accumulate my savings, and this is what it says money saved. So I'm accumulating 4 and 4 and 4 and 4, and then 0, 0, 0, and then 4 and 4. Why 0, 0, 0? Because in the slow version, I'm not able to save anything. This is the maximum I can pay, so I cannot save anything from there. So in total, the sum of the amount of money saved is $24, which is the sum of 4 and 4 and 4 and 4. We have 6 4s, so that's $24. Okay? Now, notice that this only works for this specific case, for this specific interleaving, and for this specific numbers of fasts and slows for operation 1 and operation 2. So this is just like the student example. At the end of the month, can he pay his bill or not? That's the same story here. If you'd like to draw an analogy between what we're looking at and the student example, it's as if this student was getting from his parents $5 a day. So at most he can spend $5, but if he spends $1, then he's going to save 4. That's what we're doing here. Okay? Every time we get an operation, we say, okay, we're going to allocate $5 to it. Let's see how much we can spend from that. And if we spend the whole amount, then we've saved nothing. If we spend less than 5, then we save the difference. And since we have fixed the numbers 1 and 5, every time we go for the fast, or we get a fast version of the operation, we are saving 4. And if we get the slow, we are forced to pay the 5. Okay? Again, I'm introducing this step at a time. I want you to get the basic idea. And then we will see how can we apply all this. Okay? Now, let's see another interleaving. Here I start with a slow version from operation 1, followed by the slow version from operation 2, followed by 2 fast ones, followed by 3 slow ones, followed by 2 fast ones. I'm going to do the same activity. When I see a slow one, at most I'm going to pay $5. This is the amortized cost. Okay? And when I see a fast one, I'm going to see 4. So if we run actually this, and at the end we ask, do we have money to actually support all of that? Well, this sequence of operations requires $29. Why? We could only save $16. So obviously there's a problem, because I cannot pay for this. Okay? Now, why I cannot pay for this? If you actually inspect the sequence of operations, we're getting too many slow ones compared to the previous slide. Here we're getting 5 slow ones, and only 4 fast ones. And given the numbers I'm using, for sure the fast ones are not going to pay for the slow ones, because the slow ones are more and they are charging 5 times more the cost of the fast ones. So here is the essence of this approach. Amortized algorithms will only work to produce the performance that we think we're getting from if the slow operation is not done too frequently. The slow operation is opening the way for a stream of fast operations, so that the cost that we save from the fast operations will enable us to pay the later on slow operation. But if you cannot pay for it because you didn't get enough fast ones, then the amortized algorithm is not really running at 2 asymptotic orders, O of n and O of n cubed. It's really running at O of n cubed most of the time. Okay? So to start having real different asymptotic orders, and that impacts the total amortized behavior, so you can claim that it's O of n instead of n cubed, then you really need to be doing a lot of fast ones and a small number of expensive slow ones. And this is what we have seen was actually the put in the hash table example before. We had a resize, if you recall, when we reached 8. We took the number of buckets to 16 by multiplying by 2. And then for a while we were doing fast operations, because every insert that will come afterwards, every put, will be done without resizing. For the 9th and 10th and 11th and 12th and 13th and 14th and 15th element in the hash table, all of them will be inserted without doubling the number of buckets. So only when we reach the 16th element, then we will double the number of buckets. And then when we double the number of buckets, we're going to go with the number of buckets to 32 instead of 16, and then we can insert the 17th, 18th, 19th, all the way to 31 without actually doubling the number of buckets. All of these are fast operations. Okay? Now, so this is the merit of the accounting method. We are going to keep a dollar balance, and we're going to track how much money we have at the end. And if we can pay for what we have done, then we will be happy. And we say that this amortized algorithm is actually giving us the asymptotic orders that we will compute. Now, again, about the essence of this. The essence of this is that I am redistributing, or another way to think of this, I'm redistributing the cost of the expensive operation on the fast ones. So you could think that of it of 2 ways. Either you are accumulating money from the fast operations to pay for the slow operation, or you are taking the cost of the slow operation and distributing it on the fast ones. And this is what amortization really means in the business world. Okay? You distribute the cost on a number of years if you are into accounting and you understand where amortization comes from, because it's a term actually that comes from accounting. Okay? We distribute the cost of an item on several years. Here we're doing the same thing, but on algorithms. We're distributing the cost of the expensive operation on the fast ones, hoping that we can actually they can pay for that slow performance. Now, one major issue that we face when trying to analyze the performance of an interleaving set of operations, where every operation has a fast and a slow version, is that we cannot assume any order nor any frequency of fast and slow. So that leaves us with a problem, and the problem is, how can we make a generic analysis that always stands regardless of what has happened in terms of the number of operations or the frequency of slow and fast or the interleaving of slow and fast? To tackle this problem, we focus in the accounting method on what's called the critical cases. The critical case will vary from one data structure to another, from one algorithm to another, but it is the moment where something drastic happens in the data structure or in the algorithm, an important event. And usually that means an expensive computation or expensive adjustment to the data structure. Now, in the case of hash tables, and that's why I like to always start with them when I talk about amortization, the critical case is known. It's very popular. It's kind of everyone's mind. It is when the number of buckets gets doubled or halved. This is pretty much the only major critical case in the hash table lifetime, that the bucket gets doubled every once in a while if the load factor upper limit is crossed, and the buckets or the number of buckets gets halved if the load factor goes below the lower limit or the lower threshold. So we will do the analysis at the moment after the critical case happens. And this is one difference between it and the averaging method, where while we were thinking of the doubling in number of buckets, but we were not doing the analysis at the moment that happens. Here it becomes critical because this is pretty much the only moment in the lifetime of the algorithm or data structure where you can stop things and ask, do I have enough dollars to pay for what has just happened? As you depart away from the critical case, you have less information, so you're not really sure. But at the moment of the critical case or immediately after the critical case, you should have enough information to enable you to ask and answer the question. So in the case of the hash table, again, there are three critical cases. Hash table is empty. There is nothing in there. Okay, that's not a very interesting case. And the other case or critical case is hash table just doubled in size. And the third one is hash table just halved in size. Okay, which is the ones I was just describing. So here are the steps. The accounting method looks obviously, somewhat similar to the averaging method, except that it's a little bit more kind of condensed. So, step number one, identify parameters to work with. Identify variables that represent the state of the data structure somehow or tell you something about the performance of the operation. Second, identify specific scenarios of interest, the critical cases we were just talking about. Okay? And you should find one critical case, obviously, per operation. Third, you state your assumptions based on the parameters and the critical cases. Deduce observations based on your assumptions. Okay, so again, you have some leeway here in the assumptions. As long as your assumptions are realistic, then you could simplify what you're working with, provided that you don't go into naive cases or unrepresentative cases of what actually happens. Now, step number 5, you will assume that I operations have been performed, and we will not assume anything about what happens in those I operations in terms of the interleaving operations, operation 1 followed by 2 followed by 3, or 2 followed by 1 followed by 3. Neither we will make any assumptions about the fast and the slow ones, how many they are, how many did we get, okay? And after the I operations have been performed, we analyze each scenario, each critical case, to figure out, do we have enough dollars in the bank to pay for it or not? Okay? And finally, we conclude our analysis. So let's see an application of these steps to the hash table methods put and get together. Now, I could also have done it put and get and find, but just to simplify it, I'm just going to do put and get. The parameters, hash tables have established parameters, small n number of entries, big N number of buckets, L is the load factor. The critical scenarios I'm going to analyze the hash table hash table has just been resized, hash table has just been halved. Okay? Assumptions. I will again try to simplify my model, so I'm going to say I will suppose that the hash table starts with one bucket. I don't have any chaining issues, so I don't have long chains, because long chains that are created from a flowed hashing function should be fixed by fixing the hashing function, not the chains. Okay, but obviously chains don't grow longer than one. It's a little bit of a simplistic assumption here, but I will assume that it will always be a constant size. It's not proportional to n. Okay. Now another assumption: put double the size of the table if the load factor is equal to 1, or if small n is equal to big N, which is the same assumption we've seen with the previous technique. Cuts the size of the table by half if L drops below a quarter. Okay, so if I have, for example, 5 keys in my hash table and 20 buckets, 5 divided by 20 is a quarter. Once I remove one of those 5 keys, now I have 4 divided by 20 is less than a quarter, so I have to cut the number of buckets by half. This is just to save memory. Now, go back to this notion of actual and amortized. The put has an actual cost of 1, amortized cost of 5. What that means is, in the fast version of put, I will pay $1. In the slow version of put, I will pay $5. In the fast version of put, I will save $4, which is the difference between the amortized and the actual. And the same thing applies for the get. Now, let's note down some observations. If at any point in time I ask how many buckets I have, I will be told some number. Let's call it big N. Now, based on this big N, I can deduce a range of the number of items I could possibly be having. It's going to be between N divided by 2 minus 1 and N divided by 2 plus 1 items. Now, why am I establishing a range? Because I don't know what happens in the past, in the history of the hash table. So it could be that the hash table has just been resized or has just been doubled. And these are the critical cases of interest to me. So if it has just been doubled, the number of items is going to be N divided by 2 plus 1. Now let's look at the figure at the bottom left to see that. If my N was 8, my big N was 8, I had 8 buckets and I had 8 entries. So my load factor now is 1 because the load factor is small n by big N. And if I'm asked to insert a new value or key into the table, I cannot insert it right away because I already at the maximum possible threshold, which is 1. I cannot exceed it, so I will have to double the number of buckets, and my number of buckets will become 16, and then I insert the new value. And as you see, this is going to be the n, the small n relation to the big N is n divided by 2 is 16 divided by 2, which is 8 plus 1, which is 9. That if I just doubled the number of buckets. Now, what about the other scenario? It happens that I just halved the number of buckets. We said we're going to halve the number of buckets if the load factor drops below a quarter, which is illustrated in the figure at the bottom right. If I have n as 16, the number of buckets is 16, and the number of entries is 4. So, apparently I kept adding elements, and then I kept afterwards removing elements till I reached to the situation where I have 16 buckets and 4 keys in the hash table. Now, if I'm asked to remove one more key, I will drop the load factor below 0.25 because 4 divided by 16 is 0.25. It's a quarter. If I remove one of these 4 keys I have, one of these 4 values, I will go below 0.25, and I'm not allowed to do that. The policy is, the strategy is, if you find yourself going below 0.25, then cut the buckets by half. So I'm going to delete 8 of the 16 and rehash my entries, and then remove the value I'm looking for, okay, that I would like to delete. What this means is the big N is going to be 8 after I cut the number of buckets by half, and after removing the element, the number of entries is going to be 3, which is exactly what I wrote here. If I just halved, it's going to be N divided by 2, it's 8, divided by 2, 4, minus 1 is 3. So if I just halved, it's going to be that, and if I just doubled, it's going to be the one above it. Okay? Now the thing is, I have no clue whether I have to double, but I'm going to stop it at the critical case. Okay? Now, because I have established a range for the number of entries in the hash table given a specific big N, what this enables me to find is at least the amount of money I have in the bank, because that will be the amount of money I accumulated between the last two resizes, the one I'm standing in and the one before it. Within this region, or in this time or lifetime of the hash table, I was actually accumulating dollars. And I try to model this by the figure at the bottom. You see, we are doing, and I'm only showing you here the doubling, but we could also think of the halving having exactly the same effect. So I'm showing you here the doubling, 3 doubling operations. So I went from 8 to 16, and from 16 to 32, and later on I will go from 32 to 64. So let's just focus on what happens between 16 and 32. When I have 16 buckets and 9 entries, why did I go there? Why am I standing there at that instance in time? Because before that I was having 8 buckets and 8 entries, and the load factor is 1, so I doubled the number of buckets. Now I have 16 buckets and 9 entries after adding the last entry I was just adding. Remember, doubling the buckets is an expensive operation. This is the slow version. We will always follow it by a number of fast operations because we don't need to do doubling anymore. So between n equal to 16, big N equal to 16, and small n equal to 9, and until we need to double again, I'm doing fast operations. Each one of those fast operations will give me, according to my model, $4 to put in the bank. When I double the 16 to 32, that's an expensive operation, and I will never double the 16 to 32 unless I have had the 16 entries already inserted, and I try to insert the 17th, and then I realize I have 16 buckets and 16 entries. I cannot add the 17th, so I double the buckets to 32, and now I have 32 buckets and 17 entries after adding the new entry. And again, I go for a while doing fast operations because I don't have to double again until the load factor goes back to 1. So with each of those, within each of those 2 resizes I'm looking at, n equal to 16, big N equal to 16, big N equal to 32, I was accumulating money. And I must have been doing also that, accumulating money earlier in the history of this hash table. Okay? Because I start the hash table with 1. And I take the 1 to 2, I double it to 2, then I double it to 4, then double 4 to 8. So all the time I'm actually accumulating money between the resizes. So, and this is what I try to highlight with the third point here. Every step we take away from this range, we put 4 more dollars in the bank. I mean n divided by 2 minus 1 and n divided by 2 plus 1. Within this range, okay, of numbers, which going back to our earlier example, it's between, the 3 and the 9, if you like, or the 4 and the 8. Within this range, we are always accumulating money. That's what I'm trying to stress in the first point here, that every put and a get either costs $1 if there is no resize, or $5 if there is a resize. So if it doesn't cost $5, then I'm saving 4. In other words, I'm saving what I'm not spending. Now, there's a very important observation here, that at any point in time during the lifetime of this hash table, let's look at the figure at the bottom right. Let's say I stop the hash table at the following configuration. Number of buckets is 32, number of entries is 22. Can I ask how many dollars, according to my model here, I would have as a minimum in the bank? Sure, because I had number of buckets equal to 32 after a resize, and the resize, after that last resize, it was 32 buckets and 17 keys. Because initially it was 16 keys and 16 buckets, I got a new key, so I decided that I have to actually double the buckets, so I made it 32 and then 17 keys. And then afterwards, I went and I inserted a number of entries until I got it now to 22. But every one of those entries is actually inserted with a profit for me or a saving for me of 4. So I could subtract the difference between 22 and 17, okay, which is the formula that you have in front of you here, and in my case here, small n is 22 minus n divided by 2, so it's going to be 32 divided by 2 is 16, minus 1 for the one that caused the resize, okay? So I will have the formula plugged in with values as you see at the bottom right of the screen. It's 4 multiplied by 22 minus 16, which is 32 divided by 2, minus 1 for the one that caused the resize, and that means that evaluates to 5. So at least I have $20 in the bank. Okay, so this is an important observation, because if I can just, you know, save this much and keep saving until my next resize, and then in my next resize, when I ask, do I have money to do it, and I find actually that the amount of money I need is either less than what I have saved or equal to what I have saved, then I'm happy. Okay, then I'm happy. This will actually work nicely. So let's run I operations and ask that question. So I will assume I operations were executed, and I will analyze the financial requirement for each one of the critical scenarios separately. So first I have the doubling scenario. Now I'm resizing the table if small n reaches big N plus 1, I exceeds the load factor of 1. So what I actually have is small n being n plus 1. So I'm going to plug in the formula I was just looking at, and instead of the small n, I will plug in n plus 1, big N plus 1. And then I will try to solve this formula. I will find it equates to $2n. Okay? Thus, resizing the hash table from n to 2n will cost me $2 big N dollars. But that is actually what I got in the bank as a minimum. Okay? That is what I got in the bank as a minimum. Now, for the halving, we'll apply exactly the same logic. We are resizing the table of n reaches, small n reaches n divided by 4 minus 1. So plug in n divided by 4 minus 1 instead of small n and solve this. And then you will find that actually you need capital N dollars in the bank. But there is indeed capital N dollars in the bank. Okay? I hope the idea was communicated, clearly. Otherwise, ask me about it in the live sessions. What you need to understand is after plugging in this, we're going to get a value, and that value is the same as what we have in the bank, because this is the formula we are using to accumulate dollars in the bank. Okay, so we are reaching to the same amount using two different approaches, one with the small n and one with the big N. So in conclusion, the bank balance never dropped below 0, and we have established that the assumed amortized cost is correct, and consequently we will conclude that the amortized cost for put and get together are constant. Where did I get the word constant from? Because if you look at the formulas for the cost, they are all involving constants. Okay, we are talking about 2 big N or big N, which is not the small n, it's not O of n. Okay, because I'm assuming that I'm going to do that for I operations. So for the cost for one operation, it's going to be a constant. These are the references for today's lecture. Again, start by Goodrich and Tamassia, and then next move on to Corman and Company. And I also have included for you a Geeks for Geeks Introduction to Amortized Analysis, and you can get the text from the included drive link. I'm also including here a reference to the math that you need to familiarize yourself with because of the summations technique that we discussed today.